In this video, we'll be looking at what it means to multiply a matrix by a vector to get another vector, and use this to rephrase a lot of the previous systems of linear equations material that we've covered. So given a matrix with columns A1 through AN, where each of our columns AI has m entries, we say that the product of our matrix A by some vector x, the way we actually calculate this is we look at our matrix A11, A12, up to A1n, A21, A22, 2n, AM1, AM2, through AMN. Each of these is our column that we're calling A1, A2, so on up to AN. We can calculate our product of this by some vector x1, x2, through xn, by just taking our x1 times the entire first column. So A1, x1, A1 is a vector. Typically, I guess we write this in the opposite order. So we'll write our constant x1 times our vector A1, x2 times our vector A2, all the way up to xn times our vector AN. And note that this is a sum where our entries are going to look like we pair up our A11 times x1 plus A12 times x2 all the way up to A1n times xn. So each entry in this vector looks like a product of terms in our matrix going across our rows. So this all the way across, we would multiply by x1 times that first term, x2 times the second term, and so on. So let's actually look at a few examples of this explicitly, and how we can talk about this idea of translating linear combinations of vectors into somehow products of matrices times other vectors. So given this triplet v1, v2, v3 inside Rm, the way we can write this linear combination, 3 times v1 minus 5 times v2 plus 7 times v3, the way we can re-express this as the product of some matrix times a vector is the matrix we create is a matrix where each of our columns inside this matrix are one of those three vectors, and we multiply that by the vector 3, -5, 7. So this is precisely our definition of what it meant to take the product of some matrix A by some vector v or x. So where are we going with this? Our main goal is to talk about translating the equations that we've considered in our systems of linear equations we've looked at previously into this idea of matrix operations. And there are several nice techniques besides just row reduction that we'll use later to envision what these solutions look like. So translating our system of linear equations, which might have been some A11 x1 plus A12 x2 plus A13 this is A1n xn is equal to B1, A21 x1, A22 x2, A2n xn, B2. This is back to our, we had m of these equations we considered in a given linear system. The way we translate this into a matrix is to let our matrix A be our matrix we're going to call this vector A1, this vector a2 and this vector an, we translate our system of linear equations into the product of the vector the vector x with this matrix A, where each of our columns are precisely the coefficient vectors of our x1, x2, up to xn, and our solution vector B are just all of our constants that each of those linear equations were being set equal to. So they're m of these guys, not n. Sure, this looks nice for later. So an equivalent way of picturing all of the systems of linear equations that we were looking at before is we're looking to solve equations of the following form. This ax is equal to b, so we're looking for x that satisfy equations such as this one. And to rephrase this, and to turn back into our idea of looking at consistent systems, anytime we have an equation ax is equal to b, we know that this has a solution. Just looking back at our definition of what this meant, we had our matrix A was equal to a matrix made up of vectors corresponding to our columns in this matrix. By definition, this ax is equal to a1 times x1, let's write this in the correct order, since x1 is a constant inside our field, times the column vector a1, x2 times the column vector a2, to xn times the column vector an. This is some linear combination of our column vectors. So our columns is AI. And so we can see that this has a solution for some x1 through xn, given a fixed b, if this b is inside the span of these a1 through an vectors we considered. So this is an alternate characterization of what it means for there to exist a solution vector x for a given system of linear equations. And we'll come back to, relatively soon, how we can go about identifying whether or not a vector b is inside the span of vectors a1 through an, and this will be very similar to the procedure we use to identify whether or not a given system is consistent using the row echelon form of the matrix. Let's look at 4 equivalent ways that we can determine whether a matrix A always determines a consistent system no matter what vector b we pick. So our first statement, this idea that for every b in A, so for any vector b, there exists an x so that ax is equal to b. That's just our definition of, given a fixed b, our system is consistent. From our earlier note, we saw that one way to define this matrix AX, or this the product of a matrix A with a vector x, was taking our coefficients x1 inside our vector x and multiplying it by the column vector a1, then x2 times the column vector a2, and so on xn to an. Given an arbitrary vector b, If these two are equal, that's precisely the definition of B being inside the span of our column vectors A1, A2, up through AN. So given this first definition, given that, fixing a B, we can find some X that satisfies that, we've precisely proved that if our system is consistent for every choice of B, for any choice of B, B must be in the span of the column vectors of A. Equivalently, since we made this choice independently, so for all B inside R to the M, by part B, you know that B is inside this span of our column vectors. So this implies immediately that since this were for any B, it must be that our span is actually equal to Rm. And note that this isn't exactly immediate. The thing that we actually have proved here is that our span contains this. It's a pretty obvious consequence of just each of these vectors AI being inside Rm that proves that this is actually equality, not containment. Since we're not going to take the sum of vectors inside R to the M and get anything outside of it. If you look at this carefully, you might notice that conditions B and C, we can actually easily get back from assuming condition C, that our span of our column vectors is the entire vector space R to the M. That immediately gives us that for some particular choice of B inside R to the M, B must be in the span. Since if the span is every vector, in particular it has this guy. Same with going from B to A. If we look really closely here, we note that since for every B that we choose, we have B is inside the span, by definition, that means that there exists some x1, x2 through xn, so that this linear combination with these particular coefficients is equal to B. So we can get back to, by the definition of this vector multiplication and by the existence of some set of coefficients x1 through xn, that we have some solution vector x. The only thing that remains to prove is that statement A and statement D are logically equivalent. And while this is going into the full details here is a little more time than I'd like to take in this video, what it essentially amounts to is proving that given some system AX is equal to B holds is the same thing as looking at the augmented coefficient matrix given by A, all of our vectors in A and B lined up together, that this is row equivalent to some row reduced matrix in echelon form. I'll call this maybe B prime. If this system is consistent, that tells us precisely what we know about the columns. So to see a little more detail in how this proof works, check out page 40 inside Lay to see a walkthrough of the proof that A and D are equivalent statements. It's pretty clear that A, B, and C are equivalent. These are fairly direct. But this one's a little longer to walk through, so I'll leave this guy for you guys to work on a little later. So just as an example, to run through some final computations to make sure you guys are comfortable with this idea of matrix multiplication, let's look at, for this system A and X up here, let's look at how we can go about computing this product of a matrix and a given vector. So this 2, 3, 4, negative 1, 5, 3, 6, negative 2, 8. Remember that we can write this by breaking our matrix into column vectors times the constants x1, x2, and x3. So this gives us our product of these two, our matrix and vector, are 2x1 plus 3x2 plus 4x3. Since we take our products coefficient-wise, negative x1 plus 5x2 plus minus 3x3, and 6x1, negative 2x2, and 8x3. So this, if we translate this into some sort of matrix equation where there's a b1, b2, and b3, this is just a pretty familiar linear system that we've already seen lots of examples of. Let's look at some alternate ways of envisioning multiplication. So you might notice here I've taken the liberty of writing up our definition of multiplication of a matrix and a vector using the product of our constants times all of our column vectors inside our matrix. You'll note there's actually a way we can picture this coefficient-wise as well. So one way to envision multiplication of a matrix is choose any row in a matrix. And so I've chosen my second row here. And then consider your vector x as a column vector in its own right. And once I've selected which row of the matrix that I'm considering, that's going to tell me what the value of my row in my in my final product here is. So we'll match up this A21 with x1, A22 with x2, all the way down to A2n with xn. So our coefficient here inside this vector, so the second coefficient corresponding to the second row, is A21 times x1 plus A22 times x2, all the way up to A2n times xn. So this coefficient B2 is precisely the term-by-term product of each of these. And note that this is actually equivalent to our definition as the linear combination of these column vectors, but for some students it's a little easier for them to envision computationally how to do this. So as a sample calculation, just a very basic one, we could multiply the matrix, let's say 3, 2, 1, 4, 7, negative 2, by the vector 1, 1. And to compute this product, we take the product of 3 and 1 and 2 and 1 to get 3 plus 2. We take the product of 1 and 1 and 4 and 1 to get 1 plus 4. And our product of 7 and 1 and negative 2 and 1 to get 7 minus 2. So our product in this case would become 5, 5, 5, coincidentally enough. So this is a sample, a way to just envision, like term by term, how to compute this product of a matrix and a vector. And finally, one of the nice byproducts of envisioning these matrices acting on vectors is they actually have beautiful properties in terms of linear functions. So given any pair of vectors in Rn and an m by n matrix, we already know how to compute something like what is A times U and A times V. And one of the nice properties of these matrices is they're linear in the sense that A acting on some sum is exactly equal to the sum as a vector of A acting on U and A acting on V individually. And this, by the way, is fairly easy to prove just using the definition of vector multiplication that we saw earlier. So this A of U plus V is precisely my column vector A1 times U1 plus V1 plus our column vector A2, U2 plus V2, all the way up to AN, UN plus VN. And now that we're just looking at scalar multiplication times a vector, it's much easier for us to see that this can translate back to a1u1 plus a1v1 down to an un plus an vn. So that's exactly, after rearranging terms, we can see pretty directly that this is a of u plus a of v. And we'll return later to see how this idea of linear actions of matrices on vectors is one of the reasons that matrices are so interesting and useful, and one of the reasons they pop up everywhere. Similarly, I'm not going to prove this one here, given a scalar product of a vector, that's the same as matrix multiplication of the matrix times the vector scaled by the constant afterwards. So between these two properties, matrix multiplication is linear. And we'll see a little more of this a little later in the course. So that's where we're going to sign off here. Next time we're going to come back and revisit the idea of spanning spans of sets of vectors and connect that to the idea of linear dependence and independence of subsets of a vector space. See you guys next time.